my goal, hopefully, here is to do as much as I can in the short amount of time we have together. So you got a big week here in terms of physics. I'll kind of summarize then where we are and where we're going. As you know, I was not here last Thursday. And when I was here last on Tuesday, I had started off with saying this much, that there is kind of two nice ways in this chapter. Those first four sections are going through that. How do you calculate the magnetic field? And we're going to give you two options. I told you option one was adding up all the little magnetic fields from little chunks. This is what I started to go through, Biot-Savart rule, and you can add them up. A second option is to use Ampere's law. And what I did on Tuesday was I tried to show you the analogy that this here is like Coulomb's law. This here is where we learned at the beginning of this course how to get the electric fields from a single chunk, a single point. And so that's what this is. This is how do you get the magnetic field from a single point. Then after we did that, we went into Gauss's law. And Gauss's law gave us a nice way of getting the electric field when there was some symmetry going on. And so you didn't look at individual chunks of charge, but you looked at the whole symmetry involved, and you ended up calculating the electric field by an argument of symmetry. And so I tried to leave you on Tuesday with this idea that Ampere's law is essentially doing the same thing. So this would be sections 1 and 2 of chapter 30. And this is sections 3 and 4. And I think Don communicated that well to you, that obviously we are not doing the test today. And we are doing it then on Thursday. And so we're going to do those 4 sections. And we will start after the test, by the way, with section 5, which I really wish the author actually started section 5 at the beginning of the next chapter. You'll see why when we get to it. But as far as your probably major concern is, you know, what are we doing up to the test? And so up to the test is the first 4 sections of chapter 30. And so you, I guess, went through, and I was talking with Don here, he led you through this calculation. I left you off here and said, all right, this is what that means. And I left you with this picture that said, okay, if you have a little chunk of back to electric field, magnetic, a little chunk of current flowing, and so this little piece here would create a magnetic field over there or over there. And you could get the magnetic field based upon this equation. And that's why if you add it all up, you will get the total magnetic field. And so ds is the direction of the current, I is the amount of current in there, r hat is the direction to the point you're interested in getting the magnetic field. And probably best if I don't go exactly through and review all of those, because I'll do that with examples. That's my big hope here today, is to show you mostly example calculations and some other things here. But this is where I left off here. And so looking at that point P up there, if I were to take my right hand, I would put my fingers in the direction of the current, there's the ds, close it towards the vector that is pointing to the field in question, and I would get out of the board. And so this makes out of the board, this makes into the board. And then Don did this. We started when I left on Tuesday, and I said, look, let's just do a long straight wire. Let's do this, what we'll call a finite wire. And you came up with this equation, right? You came up with, after going through a bunch of calculus here, this picture here. And let me show you in 2 ways, because Don was telling me there's a little bit of confusion on the angles. One way of viewing it is what I will call theta 1 and theta 2. And if you measure everything from theta 1 and theta 2, which I've labeled here as theta 1, theta 2, so here's the wire. It starts here, it goes to there, okay? And so this is where the current is. I'm trying to improve my picture here. But this is theta 1, this is theta 2. You end up with saying this then is the magnetic field from a straight wire. That's the result of a bunch of calculus. On the other hand, sometimes it is convenient to measure the angle from coming down from the apex. You'll see that well if on your homework you get something like this. Here is a square or rectangular loop. What is the magnetic field at the center? Well, if you're going to do it at the center, you're probably going to say draw a little line out to there, a little line out to there, maybe draw a perpendicular and measure your angles there. So in that type of problem, I would say the alphas are very convenient. In the problem where you're actually doing the calculation, since this is the angle between the S and ds, I would say the thetas are convenient. So whichever way works best for you, and Don had told me that a number of people have asked them both ways, and now I understand why, because the book gives it in terms of alpha, and the solution manual you guys have been looking at tends to do it in terms of the theta. So I thought this would be a good place to start today by showing you a picture of one, labeling them in terms of theta 1 and theta 2. And so this picture is actually a picture in an older edition of your book. Your current edition, so this is the 6th edition of the book, but the 7th edition of the book has that picture in it, and so it labels it from the top, and so hopefully that makes it clear. And so, like I said, I personally like the thetas. The alphas are okay. Like I said, they kind of have an advantage when you are actually looking then at a rectangular loop and you want to find the magnetic field. And that's where they really come into their own. The one that you got to be careful with, though, is that this convention, when you derive this, is that swinging this direction. So if you're kind of looking down and swinging this way, right, in kind of a clockwise direction here, that's positive angles, and this is negative angles. So we would have to label alpha as a negative angle. And to me, that's hard to forget. It's a convention that I need to remember. But I thought I would point it out. What if I made this an infinitely long wire? What would this equation become? Yeah, if this wire was infinitely long, what would theta be? Theta 1? 0, right? Or if you like it the other way, what would alpha 1 become? Yeah, 90 degrees or pi over 2. Okay. And so this equation would become mu naught I over 4 pi a, and this would become a 1. Because cosine of 0 is 1, or sine of 90 degrees is 1. And then if you made the wire completely infinite in the other direction out here, what would theta 2 become? Okay, 180 degrees or pi. Or how about this one? What would this become? Okay, 90, negative 90, right? And so this would again be negative 1. All of that reducing to mu naught times I over 2 pi a. So a very useful and convenient equation is what is the magnetic field from a long wire? Okay, and you'll see that again and again and again, especially as we get into the next 2 chapters where we need to use the magnetic field to continue on where we're going. Obviously, this chapter is about how do you get the value of the magnetic field. The next chapters are going to be using the magnetic field. All right, but this is for a wire. So we've got the equation for a finite wire. We got the equation for an infinite wire. After you did that, you did a circular loop. And so I trust that Don kind of grabbed this and said, all right, what is the magnetic field from a circular loop? And again, in the interest of time to get to the examples, let me not repeat that, but let me point out then that maybe I'll get a chance to do it when we do examples. I should have pointed out at the beginning is the review today, this afternoon. Don wanted me to mention that he'll go ahead and do it magnetism first at 2:30, and then going on to circuits. And so kind of the reverse order of what we learned. And so that way, if you wanted to know one topic more than the other, you could come either at the beginning and leave, or come later and whatnot, or stay for the whole thing. Is that a question?
Are you going to be recorded?
Recorded?
Yeah, like you record all your entries. So now.
Probably, it's not the plan. I can say something to Don, but no, yeah.
So in the circuits one, are they covering things like the pole voltage and the circuit velocity, resistance, and all that?
Yeah, whatever. Yeah, that would be that chapter 29, yeah. Well, anyways, again, let me just kind of skip right through that, but say this then is the equation that Don worked out, again, when he did the integral around a loop. And that's kind of nice. A lot of times we are curious right at the center of the loop. So here's a special case when x equals to 0. So again, you'll see that a lot. Not only this chapter, but the next chapters. What is the magnetic field right at the center? So this is along the axis, off plane by a distance x. This is right on the plane at x equals to 0. Then Don said he didn't get too far, but he got started then into Ampere's law. And that's where kind of I thought, okay, that's where I'll pick up here. But I did want to point something out here. Let me jump back to this picture here. Is not only are we calculating the magnetic field, but there's always a question of what direction is the magnetic field. And I'm going to need to know that in order to do Ampere's law. So before we get over to here, let me just pull out my right hand again and say, okay, how do I get the magnetic field, the direction of it right there? Well, one way, and I say one way because I want to make sure you see the second way, but one way is to say, well, isn't the direction of the magnetic field coming from the cross product? And that's the part I showed you last Tuesday and mentioned it again today, that if you take your right hand and you put your fingers in the direction of the current, so there's the ds, and you close your hand towards the dr, your thumb is that cross product, right? And so the magnetic field would be out of the board. If we looked at any points down here, we would say, well, there's the ds and the r hat would be down, so we would turn our hand this way and we would get into the board. And so the magnetic field here is coming out of the board. The magnetic field here is going into the board. If I pick a point that's straight out over here, what direction would the magnetic field be? Well, there would be ds. dr would be that way, right? So I would get a down. So out here in front of the screen would be a magnetic field that's down. Below the wire would be into it. Behind the wire would be up. On top of the wire would be out. Do you see a circle here? And so the picture, hopefully you have in your mind, is the magnetic field from a wire can be gotten by a second option. And that second option is a result of saying it's this equation is how you calculate it. And to get the direction, just simply do this. Take the wire. Here's the wire. Take your right hand. Grab the wire with your right hand, extending your thumb in the direction of the current. Now look at your fingers. What are they doing? Aren't their fingers wrapping circles around it? That's the direction of the magnetic field. So instead of actually doing the cross product, although don't forget that, you're more than welcome to continue to do the cross product, another nice way to get the magnetic field is just simply, okay, here's a wire, grab it, right hand, thumb in the direction of the current. And your fingers will give you the direction. So this is showing the direction of the magnetic field. So if I had a loop like this, and the current was going this way, I have just told you that this is the equation for the magnetic field as you worked out last Thursday. How do I get the direction? Well, there it is. I guess I would say at this part of the wire, couldn't I grab my hand with my thumb in the direction of the current this way? And so that would mean it would be making loops like this. So on this side of the loop, the magnetic field would be that way, right? And on this side of the loop, the magnetic field will be that way. So let me give you a third option, in case two weren't enough for you. If you got loops, here's a good way to get the magnetic field. Instead of using your thumb as the current, which works really nice for wires because they're straight wires. And then your fingers give you the field. Switch. For loops, let's use our fingers as the current. And what does our thumb give us? Field. And so as I curl my fingers with the current, my thumb gives me the field. Did you catch that? Let me just review those two, right? Straight objects, use your thumb as the current, because your thumb's straight. The field is curved. So your thumb is the current, fingers are the field. Fair enough? Curved objects. Use your fingers for the current. They switch roles. And your thumb will give you the field. Fair enough? But because they switch roles, they can easily get confused. Okay? So circular currents, use your fingers for the current. Straight currents, use your thumb for the current. And your fingers give you the field. Okay? And so either of those two options. Or, when in doubt, just go back to the cross product. You know, it is ds cross r hat. But sometimes that takes a little more thought. These are less, I think, working with. Okay? So, Don, I think, showed you that one, and then did one quick calculation, or two quick calculations. He then said, all right, let's then use Ampere's law and do something like this. Let's have a wire carrying a current, and let's calculate the field outside this infinitely long wire. And the point of this calculation, and I'll just kind of review what Don did here, is to say, I'm not trying in any way to find the equation for an infinite wire. Don't I already have it? And so, if I try this second technique, Ampere's law, shouldn't I get the same thing? Right? And so here's what Ampere's law says. You can see it kind of looks like Gauss's law. Didn't Gauss's law, maybe I should put Gauss's law back on here, but didn't we say E dot dA over a closed area equals, well, let me stop right there. Do you kind of see the same thing? It's a B dot ds. Now there is something very different here. What does the S mean compared to the A? Yeah, it's a line integral, right? It's over some kind of straight line. So here was over a surface. So we call this a Gaussian surface. This one we will call an Ampean loop. Okay? And so you can see in this drawing that as we have a current coming this way, if we draw loop number 1, that is our Ampean loop. It is not a surface. It is a loop. It is a loop around the wire. It's a circular loop around the wire. And again, just like Gauss's law gave us the electric field by saying how much charge is inside of our Gaussian surface, our magnetic field is going to be found by saying how much current is inside or going through the middle of our Ampean loop. Exactly. All right. And so here's the part where I want to pick up. And like I said, Don said he did some of this. He did outside, inside, but he didn't do the toroid and solenoid. So those are really the last parts of this chapter. So let me just kind of quickly repeat this one. And hopefully you'll get the idea that this is very much like we did with Gauss's law here. Because here's the first step. That first step, just like it was for Gauss's law, is to take the dot product. And when you take that dot product, you of course have the magnitude of the magnetic field and the angle. But the purpose of that is if you pick the correct Ampean loop, just like back here, if we picked a correct Gaussian surface, we could make a physics argument, even though we don't know the value of the magnetic field, we can make an argument that it's the same value on the loop. And so here's that same idea. Imagine yourself anywhere on this loop. You stand here, and as you look, you'll see a current distribution. If you stand here, you will see the same current distribution. If you stand here, you say the same current distribution. Knowing that the magnetic field comes from the current distribution, our argument is that B is therefore a constant throughout that loop. Okay? Direction. All right, well, direction, we have to know a little bit about it. That's why Ampere's law kind of follows this. But if we go back to Biot-Savart, we do know that the magnetic field that is created is perpendicular to both A, the direction of the current, and B, the direction from that current to that place we're trying to find the field. So with that in mind, if you look kind of at this picture and you see yourself right here on this Amperean loop, you can jump over here and say, well, wait a minute. The current in this picture is supposed to be coming out towards you. Then I am moving perpendicular to that. So what direction would the magnetic field be? Oh, I like that. Magnetic field BB even, right? All right. But this is that third perpendicular. And it goes back to that same right-hand rule that I was saying. If you imagine this as a long straight wire anyways, when we did just a moment ago here, it was to say, imagine this wire, imagine grabbing it with the right hand, imagine putting your thumb in the direction and getting a little circle around there. So this magnetic field should be in the what I would call tangential, if you will, to the circle. So as I go to add up around the loop, B and ds are in the same direction, aren't they? And so that's cosine of 0. And so now I can finish the calculation by just writing this as the integral around the loop equals to I. The current inside is all the current, and around the loop just becomes 2 pi r. And I'm going to use an r because their author's picture has an r. But if you remember back here when we did the finite wire, we used a for the distance away. So hopefully that's not confusing. But in either case, don't we end up with the same equation? So again, the point is not so much to come up with this equation. This is the same equation if you replace the r and the a there. And of course it is, but the point here was to do it in terms of what does this mean. And that would be outside. What about loop number 2? What about inside? Yeah. And then hopefully you got that same logic. That, look, if you take the Amperean loop number 2, you could argue the same symmetry that we argued on the outside. That is, anywhere you imagine yourself standing on loop number 2, you can look around you and see the same effect of current. Hence, whatever magnetic field is created at that point, which I don't know what it is, that's what I'm looking for. But whatever it is, I know it's going to be the same value everywhere on that Amperean loop. And hence, I pull it out of the integral like I can do with any constant. And then likewise, direction, going through the right-hand rule, I can know that it is perpendicular, and what I mean by perpendicular to r, so it's in the direction of the blue line here, tangential to the blue line, so the angle is 0 degrees, and so this side really comes out to be the same thing. So whether we're inside or outside, it's kind of that same argument here, same magnetic field, same direction, all that remains the same. The thing that changes, though, is the other side of the equation. How much current is inside of my Amperean loop? Can you see it's not all the current now? That's the real key here. How much is inside? Yeah, and probably the best thing to do is to add it up and say, all right, the total current is the current density added up over that area. And so I will start maybe with what is the current density at the center and add it up, 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 add it up. Now, in the easiest case, and Don said this is what he did, the easy case, the current would be uniformly spread out in that wire. So what would I say about the current density? The constant, right? And so I would just pull the J out in front. In fact, the J would actually be the total current divided by the total area. And the total area is pi capital R squared. Not to be confused with little r, because when I do the integral, what am I adding up in terms of the area? Wouldn't this be area? An area of what?
The inside.
Inside of what? Yeah, it's inside the Amperean loop, right? I'm adding up all the current that is inside the Amperean loop, not all the current that is in the wire. If it was all the current that was in the wire, I would just come back here and call it I. That's what we meant here. And so that's why I use a pi little r squared here, but I use a pi capital R squared here. Okay? Because again, it's how much current is inside. Which now means I can do some reducing here, starting with the pi's. Anything else? Guess there's an R over there and an R over here. And so I end up with mu naught times I 2 pi R squared little r. And so we get the magnetic field 0 at the center of the wire and increasing in a linear fashion until we get to the edge of the wire. When we get to the edge of the wire, the magnetic field then tapers off with our 1 over r value, increases linearly with our 1 over r. And so this is new, and when I say new, I know you saw it, but it's new in the sense of we did not do that with Biot-Savart. In fact, it would not be an easy calculation with Biot-Savart. So this is a good example of how easy this calculation can be with Ampere's law and how challenging it can be with Biot-Savart. And so we've got both because one way is often much easier than the other way.
Would you say that a constant current density is the most common in real circuits?
Yeah, sure. There's some inductive effects for AC that maybe I shouldn't necessarily address, but I'll say yeah. Because they do, there are a bunch of negative charges they want to spread out. And so unless there's anything changing or going on, there's no reason they don't want to get all spread out. Yeah?
So is the left side for number 2?
So this is the R less than capital R. So this is the Amperean loop number 2. And this is Amperean loop number 1. This is for R greater than, little r greater than big R. So outside, we got the same as before. Inside, we hadn't done in terms of Biot-Savart, but this is a good way of doing the inside. Yeah?
The dA is the change in area of the surface?
The dA, let me see if I can draw it here. Here's the wire, radius capital R, okay? The dA is a small area that's inside the Amperean loop, so that when I add up the current density and the area as it gets bigger and bigger and bigger, I eventually get the whole current that is inside the Amperean loop. And so this dA is kind of the area of one of these rings. And a ring plus a ring plus a ring plus a ring plus a ring eventually gets the whole current that is inside the Amperean loop. But the limit of my dA is only to the Amperean loop. I only want to know what current goes through the Amperean loop. That's what tends to make these problems a little more easy to calculate. But we saw that same thing with Gauss's law. Even though we might have had charges on the outside of our Gaussian surface, we didn't need them in that equation. That's the neat part about it. And so we can ignore all the other stuff that is outside of our Amperean loop, or ignore all the stuff that's outside of our Gaussian surface. That's what made the calculations nice. Now, that's not to say they're not part of the overall puzzle, but it is to say that whatever field you get from the stuff on the outside is balanced by the field from the other stuff at the outside. And so if you actually did do an integral, they all come out to be 0. That's the beauty and the shortness of Amperean's loop here, and of Gauss's law, is all those other things outside are gonna cancel off. They may not be easy to show that they cancel off, but they will, and that's why we like to do Gauss's law when Coulomb's law looks hard, and that's why we like to do Ampere's law when Biot-Savart looks hard. Okay? Well, let's try something new then. Something you didn't see, and that would be another good example of Ampere's law. Let's use this particular shape. I grabbed some just for illustration purposes. These are referred to as toroids. Here is a nice big toroid. You can see the electrical wires that plug in with our banana jacks, and the current goes through. Unfortunately, it's covered with some red tape, so you can't see the numerous wires that go around it. Here's a smaller toroid. This one you can see the wires. They're all glued together and painted red, but you can see the wires. So I thought these would make two nice toroids to pass around. And here's a toroid straight off of a circuit board here, and so I go, hey, let me grab these three, but throw them around, and so when I use the word toroid, because that's probably not a very common word, that you'll catch that. But I hope you see it in the picture. And in fact, here's tomorrow's lab. Tomorrow's lab, you are going to build a toroid and some other things. Well, one of them, in fact, I should say, one of the things you're going to do in tomorrow's lab or Thursday's lab, which is the reason I wanted to bring it up. What did I do with that long wire? I lost it. There it is. Okay? But one of the things you'll do in tomorrow's lab is you'll first just hook up your power supply to this long wire right here. Okay? And we actually won't use this. We'll just use a wire, and we'll have somebody on your team hold it. Okay? Hold it. Actually, we'll have you hold it this way. But hold it. And then we'll take that power supply, and if you remember, we'll just crank it up to full power. I think we get a whole 5 amps out of it. But you're supposed to measure the magnetic field. Okay? And according to this, the magnetic field should drop off with a 1 over r squared value. But the second experiment, actually I think you do that one third. I think you do this one first. But you're going to build a toroid. And you're simply going to take this metal slinky. You're going to hook it on one side, wrap it around, and there's your toroid. Okay? And you will hook up your electrode, and hopefully it'll look something like this. Current will go in one side, current will go in the other side. As you'll see, this is a good way of getting a very strong magnetic field. So toroids and solenoids can make some strong fields. And that's what you're going to see. So I say all that with this invitation. I know you have the test coming up Thursday. I know the material we do in lab is about this stuff. So those of you who have Thursday and say, you know what, I really want to get a better understanding, I want to get my hands dirty, you're more than welcome to attend either of the Wednesday's labs so that you actually do it before you take the test on it. And the reverse is true also. For any of you on Wednesday then who say, you know what, I got the conceptual idea pretty good, I want to have more time to study, all right, come Thursday. I hope that doesn't mean all of you come on Thursday, because that'll be a little too many people. But if you want to do some, if you even can, if your schedule will allow, you could do some shifting around there. And so take advantage of whatever's going to work best for you. And I wanted to throw that out there.
Are toroids going to be on this test or the next one?
Yeah, this one too. Yeah, this one, because this is another example of Ampere's law. I want to, like I said, basically I want to do four, I guess. These are the first two. A wire outside, wire inside, toroid, solenoid. And then I'll jump into examples at the end of the chapter here. But let's do the toroid. The toroid, again, nice strong magnetic field is the whole purpose of it, but watch what happens here. If I draw a picture of that toroid, or maybe I won't draw too sophisticated of a picture since we already have a toroid picture up there. And so maybe I'll just do what your author has, which your author has the current coming in this way. So here's I. He then wraps it around this, can I say donut shaped? All right, this well, maybe I should say toroid. Sounds more sophisticated. But here, is this toroid, right? You laughing at my picture?
No, I was just detecting.
All right, so here's the toroid with it coming in here. But let's look at then some ambient loops. 3 in particular. The most significant one is actually in the internal parts of the toroid. But the question could also be asked, what about the magnetic field outside the toroid? And what about the magnetic field in the center part, which, if you think of it a donut, I'll call it the donut hole there. What is the magnetic field in there? But let me start with, and maybe I'll change colors and do what is the most significant one first, and that is what your author does. He takes a blue line and he goes around in a circle inside of the toroid. All right, so this is my ambient loop. The ambient loop is at some distance r from the center. So again, notice how we measure it. He calls it r. There it is, right there, r. Okay? He also says there is a radius b and c. And b is the smaller one. So he calls this radius b, and he calls out here radius c. So I am looking at an ambient loop that is greater than b but less than c. To make it clear, I am on the internal parts of the toroid. I'm on the chewy part of the donut. You know, this is the good stuff here, right? All right. Outside of the donut and in the donut hole, there's not much of value. I suppose you may argue there's not much value in the donut either, but it sure tastes good nonetheless. All right. But there's the value in the interior part here. And so that's the part I want to do first. And again, let me just apply Ampere's law. Here's Ampere's law. The integral of B dot ds is equal to mu naught times the current that goes on the inside of the ambient loop. All right, well, let's start with the left-hand side. Okay, left-hand side, just like we did for the wire, little harder perhaps. But over here on that left-hand side, I would say, first thing, dot product. Take your dot product. All right, so I've got the B ds cosine theta. But again, this is the one that we argue from symmetry. Look carefully at this, particularly the value of B. Is it fair to say that no matter where I am on this ambient loop, B would be the same value, right? Because if you stand here, the current around you, which is kind of looping around your head and around the whole donut thing, would look the same as over here. So my first step is to pull the B outside. Exactly. Closed loop, closed loop. Question? Yeah.
Well, I would say that's not true because the other one outside.
Oh, okay. So if I could magically let it come in like that, how's that? Yeah. So let's do this then. Let's just talk about this effect. Then these are long straight wires. So wouldn't the total magnetic field be the combination of what I'm about to calculate plus 2 long straight wires? And don't I know how to do long straight wires? Right? Okay, so I will say fair enough. Also, what you'll see in a minute is the field from this part is so strong that add or ignore this part is irrelevant. Yeah. So, yeah, but as soon as I pull that in, I do fill up the symmetry a little bit. Okay, now, like I said, forgetting that part, what about my angle? Well, like I just did a minute ago with the Ampean loop, this again takes some symmetry arguments here, but what direction would the magnetic field be? Well, remember I gave you 3 options for finding the magnetic field? One was that cross product, one was for straight wires. These have a lot of curved wires, so let's do the curved wire. Here's a loop, a single loop. Now I know this has many loops, but let's look at one loop. Again, take my right hand. How do I find the direction of the magnetic field? Curl my fingers with the current. Direction of field would be with my thumb. So, as I look at this problem here, it looks like the current goes over the top and underneath. Curl. And so the magnetic field at this point would be this way, would be this way, would be this way, would be this way, would be this way. And so I claim that the magnetic field, as indicated in that picture, right, is right through that loop. Well, that's maybe a bad example because that one's not curved. But it would be a circle inside the internal parts of this toroid. And that would be the direction of the magnetic field. Now the reason I care about that is because what I want to know is what is the direction between the magnetic field and the loop. So in this case it's 0. Exactly. And so this side of the equation becomes b 2 pi r. Yay! And so again, hopefully the integral itself is not hard, and the answers aren't hard, except the argument to get there is hard, the symmetry of that. And you've got to look at the B field, and you've got to look at the angle, and you've got to look at the dot product, and you've got to look at the other side of the equation. Because now as we move over to the other side of the equation, we've got this. How much current goes through my Ampean loop? Well, my Ampean loop goes out this far, doesn't it? So the current that goes over the top and then tucks in, doesn't that one go through my Ampean loop? Then as it tucks in and comes back up, that one doesn't go through my Ampean loop, right? Then as it goes over the top and tucks in again, doesn't that one go in? And that's inside of my Ampean loop. So that one, that one, that one, that one, that one, that one, all of these go into my Ampean loop. All of these coming out have nothing to do with my Ampean loop. If it did, I would say, well, some go in, some go out, equal amount go in, equal amount go out, and I would say the net current in my Ampean loop is 0, but that's not the case, is it? See how some go in and the rest of it that comes out is not within the Ampean loop? So I'm going to put n times I, where n is the number of loops. How many loops do you have in this toroid? If you got a good look at those ones passing around, you will see 2,000 loops in that big one. There's what gives you the real strength of the toroid. It's really the number of turns. That's why anything that is wrapped around with all these turns tends to be really, really strong fields. And so you watch the lab we do this week and next week and the following week. When we keep using the magnetic field, we always have these wires that we wrap around. When we've got these wires that are just straight, we go, small magnetic field. Too small to worry about. Which is really your question back here, is that if this number is 2,000, then when I calculate the magnetic field from these guys, this toroid in here is making the field 2,000 stronger than that one. And these are even kind of far away, so even more so. And so I'm not going to worry about the lead wires connected in, and you know, at least in my first model. You know, maybe in model 2 I'll improve it and get a little more information about the strength of the magnetic field. And so that's the real key. And so when all this is said and done, I get the equation for the magnetic field from a toroid. I personally like to memorize it this way with the N out in front. I don't know if that helps you. But the N out in front is because look at the rest of it. What does the rest of it look like? Doesn't that look like the same equation for a single wire? And so really all you've done is just used the multiple loops to amplify the field. And so you're saying the field is N times stronger. And like I said, with 2,000 loops, this can be many times stronger. Yeah.
And that's the same value between B and C?
Oh, now I should point this out that I have, if we look a little closer at this, notice that the magnetic field does change with distance, right? But also, notice my logic is only valid between B and C. And so if I was making a plot of the magnetic field, or maybe I'll put it over here for my grand finale. But as I was plotting the magnetic field with distance, and I put B and C, I have only found the magnetic field in the interior parts of this donut, right? And so I see that I get a field that is not uniform, which is kind of the bad thing about the toroid. But the good thing is I see it is really strong. But I do see it changes within that toroid. And so where would the field be the strongest? Well, I guess it would be up here where the radius is B. And then as it gets further out, it gets weaker and weaker till it gets to C. And so it has this 1 over R value that I'm going to plot right there, and what you're going to measure tomorrow and plot. That's why I have you get out the toroid and the Hall probe, and you stick it in and out, and you measure the field, and then you plot the field, and you see that 1 over R value within the interior part of the toroid.
So if you had one loop, it'd be identical equation to the wire.
If I had one loop, this argument of symmetry would break down. So I wouldn't try to use this for one loop. Then I would go back to what we did. We did do one loop with Biot-Savart.
So how many loops do you have to have?
Well, I guess the answer would be exactly correct if I had an infinite number of loops that were infinitely thin. I never have that, right? So then I have to break it down and say, okay, how close does the real toroid compare to this? So again, I'm back to that same dilemma. I will do this as a first good approximation and realize it's not perfect. If I want to break it down into wire space, wire space, wire space, then I better do Biot-Savart and I better add this up. And that integral looks pretty hard. Probably will break it down into a Riemann sum and program it into the computer and do a numerical calculation and get my answer. And so I will probably, this will be generation 1 and then generation 2. And so same thing with your academic learning. This will be your first class on E&M, but then you'll transfer, and so now you'll do harder problems and harder problems and harder problems. Don was telling me that somebody asked after class that when he got done calculating the magnetic field along the axis of symmetry, they said, well, what if you were here? Which is a great question. And you would just have to set Biot-Savart. It'd be a much harder integral. I don't even think there's a closed form to that, so I'd have to put it into my computer. I'd set up a Riemann sum. And so it would not be something we would do this semester, is what you would do next year. Would you have your junior level E&M class? What if you're off center? And so, again, that's what you're asking. And so, I know some of these problems can look pretty hard, but we do overly simplify them. We do. We give you the easiest we can for magnetic fields. They're just not easy to begin with, but they're the easiest we can start with. And so that's what we've done. How about we go inside of what I'll call the donut hole area. Let's look at R less than B. Now, that would mean an Ampean loop that is in here. And maybe in the interest of time, let's just see how does it change. I mean, let's start with this and put it over here. With the left-hand side, well, this would be the same, right? This is Ampere's law from the beginning. And I don't see anything that would be different on the left-hand side. I mean, I would start with the same Ampere's law. I would take the dot product. I would take a symmetry argument that anywhere you go along that Ampean loop, the B field should be the same. I don't even know what it is, but I know it should be the same. And the angle should be 0, and so I still get the 2 pi r. Okay, fair enough. How about the other side? How much current goes through my Ampean loop? Yay! So there's the really nice thing about a toroid. Not only did I get a very strong field in the internal parts of my toroid, how much did I get outside, well in this case inside the donut hole? 0. And so my field is well confined. Okay? And because of that, hopefully it won't interfere with other parts of my electronics or whatever it is I'm trying to build here. Okay? And so there is no field in that area. And then likewise, how about if we try R greater than C? And so I take an Ampean loop that is larger than the big radius on the toroid. And again, the left-hand side is still going to be the same argument. B times 2 pi r. We're going to say the field, whatever it is going to be the same value. But now we look at how much current goes through that one, and ignoring this effect, wouldn't you say that one goes in, that one comes out, in, out, in, out, in, out, in, out. How much? 0, right? And so the magnetic field on the outside of that toroid is 0. And so these are the nice designs of toroids, and why we like to use toroids is that they make very large fields on the interior stuff, and anything that is inside the donut hole or outside of the toroid is 0. And so my 0, big, weaker, 0, outside. And so that's approximately what you will get. Okay? And of course, don't be surprised tomorrow in lab when you actually go to measure this if you don't get, you know, something that looks like this. 0, 0, 0, you know. And obviously there's going to be transitions because we don't have infinitely thin wires and infinitely number of turns. And so you're going to see the real effect because this is your toroid. This is not an infinite number of turns. There's about 50 turns here. But when you build it, you're going to see something like that. Which is why in the lab I ask you to plot the theoretical field and your measured field and see how they compare.
Is that a curved line or a straight line?
B and C?
Between
In the black?
is it curved? The red one.
Yeah, it is a curved. It's a 1 over r value. It's technically, I guess, a hyperbola in its shape. Well, as I said, there's 2 shapes I wanted to do in this first hour. I wanted to review a little bit and do 2 shapes and then do as many examples. But this, as I said, is a really nice field because they're very strong. They're confined to just the interior parts. But what's disappointing is it's not a uniform field. Right? It does change. You get really strong ones on the smaller radii and weaker fields as you get out. If you change the design a little bit, you will change the pattern of the field. And so the toroid and the solenoid, and maybe here's a good model of the solenoid, and that's why this other design is out here. This is our model of a solenoid. Solenoids too can make strong fields. Okay? What their advantage is, as you'll see, is they make nice uniform fields. So their field's not quite as strong, but it's uniform. That's nice. They're kind of zero on the outside, but only if we approximate them as being infinitely long, and there really is no solenoid that's infinitely long, so the field is eventually going to wrap out of the back end and back inside. So they unfortunately have that disadvantage, but you can kind of see here, here's what the author is trying to say, and he puts the purple for the current, and so looking at it this way, he's got the current going, if I'm looking at it kind of this way, this is the bottom part, he's got the current going down and then up and then down and then up and then down and then up and then down and then up. And he says if you grab one little section like this one, and you think of this little section as a straight wire, and you grab your right hand, putting your thumb in the direction of the current, wouldn't this little section make a magnetic field around it? And that's what he's trying to show right here. Or right here, or right here, or right here, or right here. Whereas then on the other side, the current is coming up. So here, 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 and here, it's coming up. So if I take my right hand and I grab this wire with my thumb pointing up, I will get circles around this way. So around that wire, around that wire, and around that wire. And of course, he doesn't show the top of the wire, but that would be the same thing at the top of the wire and at the bottom of the wire. And so at the top of the wire, I would get little circles like this. But if you'll notice that the circles here point that way on the interior part of the solenoid. The circles here point the same direction. The circles at the top point the same direction. The circles at the bottom point the same direction. Everything on this solenoid points that way, which matches our other property I said of getting the magnetic field. It's kind of nice. If you have something going in a circle, take your right hand, curl it in that direction, and your thumb will point in the direction of the magnetic field. And so I claim that this shape should make something that your author has drawn here, where this green lines are the magnetic field. So these are the magnetic fields right down the center of the solenoid. Okay? And of course, you can kind of see that they're going to add together. The question though does, as you add across, does it keep the same value of the field? And surprisingly it does. We are going to have to do an approximation like we did with the toroid. We're going to have to say, take this and wrap it real tight. And so a real solenoid may have space between them, but you can see them getting closer and closer together. So here's some good examples of we'll be using in the lab. Here is a toroid with 440 turns on the wire going around. This one has 180 going around, but they're a lot of turns and they're nice and straight. I'll pass these around too, and you can look at those. But hopefully in the few minutes we have here, you will see that this too makes a very strong field. And approximately zero on the outside, but only if you say it goes to infinity. So it's not quite zero. So in that sense, the toroid is a little bit nicer. But also, you will get the real advantage of the solenoid is the field will be really close to being uniform within there. And if we make an infinite approximation, we will get a uniform field. Yeah. Oh, good point. And that's exactly how they do these. One of the problems I hope to show you here in a second is a Tokamak. And they've got a pretty good radius on it. It's like 1.8 meters in radius. But you could even make it as big as this room, let's say. And so now you're looking at maybe a radius from 5 meters to 5.5 meters. And so there wouldn't be much change in the field. And that's what this big guy is designed to do. It's got a rectangular cross section. And you can kind of see that from one edge to the other, there's not much change in R. And so because of its big inner diameter and small width to it, it's got a pretty close to a uniform magnetic field. Yeah.
It would act more like that.
And so it would be more like this without the effect of the field being on the outside. So this is nice. This is that one's out of an old nuclear magnetic resonator. And the idea was you wanted a strong field, you wanted it uniform, but you really didn't want any field outside to interfere with the other parts that are going on in your scientific measurements, and so it was real important there. So and that's how they designed it. Said, okay, what we'll do is we'll make it very strong, we'll make it approximately uniform, but we'll really make it captured inside by wrapping it around on itself. And you can see that the magnetic field's got to wrap around on themselves at some point. So if they come in here, they have to come out, unless they're infinitely long, right? Because there is no such thing as a monopole. And no thing as a monopole means the magnetic fields got to come back and touch themselves. They cannot just start or terminate anywhere like our electric fields can. Our magnetic fields got to make a closed loop to it. All right, well, so doing this last calculation before we get into examples, your author does this. Oh, actually, here's a nice picture. He shows probably the more realistic magnetic field from a solenoid. That it is not exactly uniform inside. It does arch around a little bit on the outside, but as we make it longer and longer and the wires tighter and tighter, as a first calculation, he says, let's do this. And so he puts the wires really close together, and in this case this is a cross section, so the current is going in, coming out, going in, coming out, going in, coming out. And he says, all right, let's make an Ampean loop. And the tough one on this might be deciding, well, what Ampean loop do you want to make? And he picks a rectangle. The rectangle is nice here, and he's got it right here. He calls this 1, 2, 3, and 4. And says, all right, let's look at that Ampean loop. Because if you integrate B dot ds equals to mu naught times the current inside, then what we have is section of loop 1, section on the loop number 2, section on the loop number 3, and section on the loop number 4 equals mu naught times current inside. So there's our 4 pieces for Ampere's law. All right, we'll start with number 1. Number 1 is this part right here. Now he doesn't say how far in you go, and that really doesn't matter at first anyways. Later on we'll talk about that, but he just goes some distance in and says let's integrate along that loop. Here's where our symmetry comes in. Stand right here for a moment and imagine yourself standing right here and then right here. If you were to stand there, and let's say the current here is this wall, if I stand a certain distance away, then as I look at that wall, I've got current going down, 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 down. If I move somewhere else, like here, I've got current going down. Doesn't it look the same? And if it's infinitely long, I have just as much current that way as I did when I was standing here. Fair enough? And so the argument being here that if this solenoid is really pretty long, okay? And of course it's a rough approximation, but again, remember, some of these electronics can be really, really small. I mean, this coil can be as long as 2 centimeters, but because I can be within a micron of the distance, that's pretty much infinite. This 2 cylinders is pretty long, and so the argument here is I can pull B out of my integral because B is the same. Now, please notice what I did not say. I did not say at this point, I will say it later on, but I'm not saying it yet. I did not say that the field was the same if I got closer to the wire, right? Because it would look different if I got closer to the wire compared to farther from the wire. Fair enough? So I'm not saying that the field is uniform in there in any way. What I'm saying is the field is a constant along that blue strip. I'm always the same distance away. Now, just to make sure I'm real clear, I will say before the problem is done that the field has the same value everywhere inside. That's the whole advantage of the solenoid, and I don't want you to miss that. Okay? But I'm not saying that yet. All I am saying is that the magnetic field is the same along that one little strip, number 1. Then I can change it to a ds. I could also say this is cosine of 0 degrees. Again, that's going to make me come back and think about what direction is the magnetic field. But we've done that a number of times. We'll do it again. But if you look at just one loop here and you curl your fingers in the direction of that one loop, your thumb is pointing that way. So this is saying the magnetic field is that way and ds is that way. So the angle is 0 degrees. Let's keep going. Look at area number 2. Hopefully this one is real easy for you. What value do you get on number 2? 0. Why? Yeah, cosine of 90 degrees. My ds is going this way, my b is that way. And that's 90 degrees, 90 degrees, 90 degrees, 90 degrees. Now we can argue out here that, well, wait a minute. Is it 90 degrees there? Well, here's where we're going to take one of two arguments. If it's an infinitely long, the magnetic field just keeps going straight and never comes out of the solenoid. So there is no magnetic field. So it's still 0 out there because there's no magnetic field out there. But another thing we could say is if it wraps around, okay, of course, then we lose our whole argument of symmetry because it can't be finite in length and still use this symmetry argument. But let's just say it was finite and I was at the center. Then again, I would say it's coming back, perpendicular. Okay, but again, that's not a good argument because again, I'm not trying to say I'm exactly at the center. But again, if it's really long and I'm somewhere near the center, I can argue that. You could even argue that I take this part of the loop and it gets further away. I mean, what if the loop gets infinitely far away? Then the magnetic field definitely would become 0 at some point. Maybe not on the first part of the wire, but definitely on this part of the wire, number 3. So there's my argument for number 3, that I'm going to get a 0 on number 2 because I'm perpendicular. I'm going to get a 0 on number 3, again, because either A, I'm outside, and this is an infinitely long cylinder. Perfect? No. Good first approximation? Yes. Okay. In fact, a few years ago, it's probably a good idea that he dropped it, but he actually did an infinite cylinder first and then a finite one, which was a summation of a bunch of rings. So you had to take the field from a ring and do an integral of a bunch of rings. And he dropped it out of this edition. And rightfully so. I think it's the next step. It's what you'll do next year when you guys transfer. It's a good, okay, what if the cylinder's not infinite? But this solenoid is infinite, so that's why I'm going to put a 0 there. And on number 4, I'm going to put a 0. So for the same reason as number 2, so there's a 0. And so the left-hand side of the equation becomes B times L. My definition of L is the length of wire number 1, and that's what they show there. So there's the Amperean loop. Then I go to the other side of the equation. Huh? The L is the length of this side right here. Because after once I've done this, I've got the integral of ds. Integral of ds is the length of side number 1. So that's B times L.
Sorry, why was there no magnetic field on 3?
Well, one of two arguments. Probably the simplest one is to say this is going to be a make-believe infinitely long cylinder. So the field never gets on the outside. Okay? And it's trapped inside. Not a very good answer, I would agree. So let me try an answer. Let's imagine this Amperean loop is not finite like it shows, but it's out here. So what would be the magnetic field if you're infinitely far from there? Okay. All right. So I think that's a little stronger argument.
So 4 is, or W is very, very large.
Yes. So let W go to infinity. And then the field on 3 would be 0. Yeah. 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 And again, you can see this isn't a perfect, this is a rough approximation here. But actually, as you'll see when you do the lab, it does measure out to be pretty good to this. Yeah.
What about L? Is that going to infinity as well?
No, I'm not letting L go to infinity. That's just the section this way of my Amperean loop. which I'm glad you bring that up, because it brings up an issue coming in just a second here, because on this side of the equation, it's the current inside the Amperean loop. And if I make L go to infinity, then I get an infinite amount of current. And that's not going to be very useful. I'm going to get infinity equals infinity. Which I guess is true, although since there's an infinite number of infinities, I don't know if all infinities are equal. Well, we know all infinities aren't equal, but that's a whole other question about how many infinities there are there. And okay, but anyway, so we know there's an infinite number of infinities, and that's a fun math lesson too. But I'm not going to let L go to infinity for just that reason. But what I am going to say is I can write this as n times the current, where again n is the number of loops, but I do not mean the total number of loops in the solenoid. You catch that? Because that was different. The toroid, I meant n was the total number of turns in the toroid. Fair enough? What do I mean here? Yeah, n is the number of turns inside of my Amperean loop. Now I should probably give it a different symbol so we don't confuse it, right? And I will here in just a second, but I will do it this way. I will take the B and solve for it by itself, write it as capital N over L times I, and then write N over L as little n, where little n is the number of loops per length. And so that's why we treat the solenoid a little bit different. We don't talk about how many turns does the solenoid have. Because in this model, it actually is going to have an infinite number of turns, right? And so it's best to describe it as how many turns per length does it have. Okay? And so there's our final equation for this unit, is what is the magnetic field from a solenoid. And so there we have it from a solenoid. And in lab tomorrow, you're going to do exactly that. You're going to take this slinky and put it on one end and put it on the other end, and you are going to build your own little toroid. And you're going to take your Hall probe and you're going to stick it in and through that. And you're going to measure what is the field on the inside, what is the field on the outside. And hopefully what you will get is what we just kind of roughly calculated, is you will get, if this is the B field, and this is the strength of the field on the x-axis, and I define x equaling 0 to be the center of my toroid, so here's my toroid like this, then I will get a magnetic field that has a constant value inside. Did you catch that? Did you catch when I finished this calculation? The strength of the magnetic field had nothing to do with where line number 1 was. And so there's the final step. The final step is, had I made line number 1 a little bit further over, or a lot further over, or closer in, wouldn't I have come up with the same thing? And so there's my final argument, that the magnetic field is going to be the same value. There is no R in this equation like there was with the toroid. There is no position there. And so you're going to get the same value everywhere in. And on the outside, we're going to get zeros. And so no magnetic field on the outside. Now again, I agree that it's overly simplified because we never have an infinitely long solenoid. We never have an infinitely close tight wound. But when you actually hook this up and do it tomorrow, you will see that you'll get 0, 0, 0, 0, 0, 0, 0. You know, and you'll get some kind of transition where you will get zeros on the outside, you will get pretty much uniform on the inside, and then in the end you'll have some edge effects. You'll have going in and coming out, and you know, see what happens as you're going in and coming out.
Why is the magnetic field the same strength in the center as opposed to right next to the edge?
I guess I would say that this field here in the center is created by both of these on each side. And so as I move left to right, I'm getting closer to this one but further from that one. I'm also getting closer to these guys, and I'm getting further from these guys. And so it's not so obvious to see, but there's a whole combination of anywhere you move, you get stronger because of these guys, weaker because of those guys. If I just had two wires, you could do a 1 over R plus a 1 over R, and this one gets stronger and this one gets weaker. And those two don't exactly balance each other.
If you had a single loop, you're saying that the magnetic field from the center would be the same as next to the edge?
No, not from a single loop. I'm saying that if all I had was a single loop, then as I get closer over to here, it gets stronger because of this one and weaker because of this one. And this one gets stronger more than this one gets weaker.
Why is that not the same over here?
Because then I have wires here, 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 and here. Here, 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 and here. So what you might be saying is, I have a plane of current. And a plane of current does not give me the 1 over R square value. It gives me a linear value, and this one gives me a linear value. So as I move in, 1 centimeter this way, I get stronger because of a movement of 1 centimeter, and here I get weaker because of 1 centimeter, and they exactly balance each other. If I have an infinitely thin or infinitely set plane next to each other.
Yeah. Isn't the magnetic field uniform because we're assuming that there's an infinite number of loops, so like a number of coils and stuff? But there's not just like one and then space, there's another one every centimeter.
Right, and that's how the math works out.
There's just
Right.
another one and another
Right, and I think it was actually conceptually, why would it be different between a single loop and an infinite number of loops? And that hopefully helps, that it's don't just think of it as one wire going down, think of it as a whole sheet going down. And a whole sheet going down would have a different magnetic field than the 1 over R value we got from just a single wire. Okay, well, although that took about 10 minutes more than I had kind of anticipated or hoped, although not too much of a surprise, and there's some other neat things in the chapter, but we're going to wait to do those other neat things and use them as part of next week. Let's take a look then at some examples here, and as many as I can do, and then Don has got about 10 of them he's going to do this afternoon also here in terms of the test review. But I wrote down like this first one, number 4. Number 4 is a good one to throw out there first, give you kind of an idea of what your homework is looking like. Maybe you've even given it a try already. Oh yeah, this edition puts it up here. But problem number 4 does this. It says, all right, now that we've done wires and loops and all those good things, let's ask this question. It says a conductor consists of a circular loop of radius capital R and 2 straight long sections as shown in the figure. The wire lies in a plane of the paper and carries a current I. Find an expression for the vector magnetic field at the center of the loop. Okay, now let's break this down. Is it fair to say that you could think of this as either 2 or 3 pieces? Doesn't this look like a long straight wire to there? Then doesn't it look like a single loop there? Then doesn't it look like another long straight wire there? Let's take the 2 long straight wires, put them together. Doesn't that look like just one long straight wire? All right, don't we know how to calculate the magnetic field from one long straight wire? So I will call this field number 1. Not worrying about the loop here for a moment, but just the long straight wire. Let me call that field number 1. We started this whole unit, or today, with an equation for a long straight wire. We did the Biot-Savart, and then we also did Ampere's law, and that's what we got. Okay, where A then is the distance away. So in our case, since we are looking at the magnetic field at the center of that loop, and they say the loop has radius R, I'm going to replace my distance away with radius R. So that's where they want me to be. So that's the magnetic field from what I would call the wire part. How about the loop? Well, we also did that one, right? The magnetic field from a loop. 2r? Mu naught I over 2r is what we had there on the board about an hour ago there. We had the Biot-Savart. We're at x equals to 0. And so when we put at the center of the loop, that is the magnetic field. And so maybe I should have put this off to the side. What is this? This whole thing was a mu naught I over 2 r squared x squared, no, cubed, that's what it is. Cubed? No. Squared. Squared. R squared 3/2 power. So some of you are looking at me like I'm crazy, but this is the one I'm using. I'm using the one that was, what is the magnetic field from a circular wire along the axis of symmetry? If you set x equal to 0 here, this becomes an r cubed over an r. That's where the r comes from. There's the 2, there's the mu naught, there's the I. And that's what I wanted you to see in this first example, is look at some crazy shapes, because all we need to know really now is circles and lines, and everything can be put together with circles and lines. So we have the equations of circles and lines, and sure enough we have this one. Now, since it is the magnetic field, we got to be careful with direction, because we got to add these two together. And so when you add two vectors, if they're in the same direction, you just add them. But if they're in opposite direction, you subtract. If they're at 90 degrees, you use Pythagorean theorem. If they're something other than 90 degrees, we got to use law of cosines or the component. So we need to look carefully also at the direction. So let me grab my right hand. Let me look at the long straight wire. Here's the long straight wire. Let me grab it with my right hand, thumb in the direction of the current. The long straight wire would make the magnetic field at this point going into the screen. Okay. How about the circular loop? Right hand, fingers curl in the direction, thumb will give me the field. It is into the screen. So both of them are into the screen. So the answer here for the total field would be the two added together. Mu naught over 2 pi r, and then mu naught I over 2r. And to make it a vector, calling into the screen the negative z direction, there would be my vector. And I suppose if you wanted to get a common denominator of 2 pi r, you could then factor out this mu naught and get 1 plus pi, and then that would be negative k hat direction for the direction of the magnetic field. Fair enough? And so my point here in picking this one, and the next one for that matter, number 5, is to say, look, use what you already know. You already know the long straight wire. You already know the single loop. Use that and put it together to get something that is more complicated. Because here's another one, number 5. It's really doing the same thing. Number 5 says, all right, look at this one here. Here we have a current that goes up. Then it makes a right angle bend. Maybe this is, the current that is in this little microprocessor, and it's, the power wire, and it goes across the outside of the circuitry. And we want to know this. We want to know, how is the magnetic field from the current that is in the power supply creating a magnetic field over here, where maybe I have another transistor over here. And so I've got a transistor on this integrated circuit that's only a few microns away to a part of the circuit that's carrying a lot of current. And my question really is how much magnetic field do I get from there? Because if it's too much, I need to change the design, maybe the placement or the directions of the current. I can't have that transistor be affected by something else. I don't want to be, having the fact that I plugged in a flash drive and the current starts flowing there to then change the memory that is in my, one of my cells here. And so I got to be careful. How does the magnetic field and the current from one part of my processor affect the other one?
Is this like one of the complications of like trying to make everything small?
Yes, it is a big complication of making it small. And that's why you hit these massive limits. And there's other complications too. Heat being a very significant one too, so I shouldn't overlook that one. And I probably should put that on a higher priority than the magnetic effects. But magnetic effects are huge in the sense of can you get faster and faster processors? And it gets harder and harder each step along the way. When I was in, your shoes back when the Earth was cooling, I remember them talking, they'd say, we're never going to build microprocessors that are faster than 1 gigahertz. I mean, 1 gigahertz is the absolute limit. There is no way, and that's what all the scientists and engineers were claiming. Well, obviously, we passed that. And interesting enough, it was a simple idea. The reason people were saying we'd never get 1 gigahertz is they were laying out all their circuit boards in a plane. And they noticed the magnetic effect. And someone later on said, you know what? The world's 3 dimensions, and we can grow our processors, and if the transistor has too much effect while it's in the plane, we'll move this in a different plane, off at different angles. And so they started designing in the 3-dimensional world, and oh wow, we can get above 1 gigahertz, And so all these barriers, come up, but they're barriers for reasons of really lack of creativity, And so it's like, okay, what can we do next? And so we keep pushing that, keep wondering if we're ever gonna, hit a barrier. It does get harder each step along the way, which is why, and they're saying the same thing now. Oh, we can't get much smaller with silicon. We got to go to carbon-based processor. And maybe that's true, or maybe someone will, figure something out of it. I think we probably just will go to carbon-based processors. I think that makes a lot of sense because we know humans and plants do it, so why can't we do it? All of our neurons are all carbon-based. We're not made out of silicon. So that's another. Anyways, so now moving on to this one. This is this question. What is the magnetic field at point P, a distance x, from a wire that comes up and makes a 90-degree bend? Okay. Well, I picked this one because of this question. How much of the magnetic field do I get at point P from this upper part? 0. Do you see that? Yeah, and that's something to keep in mind, especially as you're designing these things, is if you really want to reduce the influence of this wire from that, say, transistor, then set it up so the currents come straight in and straight out. You get no magnetic effect here. So you could argue then that the magnetic effect only comes from this guy here. So if I were to call this magnetic field number 1 created by wire number 1, and magnetic field number 2 coming from wire number 2, I can say the magnetic field from number 2 is 0. Okay? And so there is no effect there. And now I can say, well, what is magnetic field number 1? Okay, so let me write this out, which also begs the question of, do you want to use the cosine or the sine equation? And maybe it's still even easier to say, well, it's just half of an infinite one. And you see that here, it is half of an infinite one. If I look at an infinite one, or half an infinite one, this going all the way back to infinity would be this angle, and that would be cosine of 0, so that's a 1. And then we would have cosine of 90 degrees, and that's a 0. And so you can see that that is the equation for half of a full wire. A full wire had a 2 downstairs, and this only has a 4. To put it in their notation, I would write it with an X, since they're saying how far away are you, and they label it in terms of an X. Okay, but again, the point of this one and number 10 also is use what you already know. We know how to do wires and circles. Take advantage of those, and so put it together. The next one, no, is it number 10? Number 10, you'll see the same thing, yeah.
When do we have to write the K vector?
Oh, fair enough, sorry, I'm not done. Yep, thank you, I just wanted to do as much as I can. But it is a magnetic field, so it has a magnitude and a direction. So I did it over here and forgot here, but this would have to be, right-hand rule, grab the wire, thumb in the direction of the current. Notice my fingers are looping around, so I would say that the field is into the board here also. So to make it complete and call it a vector. It is in the negative k hat direction. Yeah. And so there's my magnetic field from that one. Number 10, and maybe we'll shift gears to do something else, but here's a nice one too. Same real effect. Here again, I have something at point P, and I want point P to be either minimum in its influence, or maybe a lot of its influence, or maybe I want to control the influence by putting a current. Because if I design it this way, you can see at point P how much magnetic field at point P do I get from this wire that's coming in? 0, exactly. And this wire coming out? 0. And the magnetic field then is affected really by this small arch, right? And we're in the plane of the circle. So going back to the derivation for the magnetic field from a loop, this is what I have to work with. But since we are in the plane, then I would say the x equals 0. And this is the one we used 2 problems ago that said this. This is the magnetic field then from a whole circle when you're in the plane. I'm not in the whole plane. I mean, I'm in the plane, but I'm not a whole circle. So what do I need to do? How much of a circle do I have, right? And it says it sustains an angle of 30 degrees. So how much of a circle is 30 degrees? Okay, if you want to do it as a proportion, 30 over 360, I like that. Mu naught times 2r. But let's see, what does that reduce to? 12 times 3 is, 1/12. So 1/12 of mu naught I times 2r, or 1/24 r mu naught I. And so there's the magnetic field. Again, hopefully illustrating the same thing, that, hey, you know a whole circle, right? You even know a circle off symmetry, so, I mean off axis. So get in the plane, which x equals to 0, and then take a fraction of the circle. So now we can do arches, right? So we can do arches and segments of a line. And so I guess in theory we could do that, right? And so there's all kinds of shapes we can do now with circles and lines and hook it all together. Right?
Is that done in the center of the
Oh, yeah, I know that's not a very good drawing for the center of the circle, but that was supposed to be a circle. That's not even much better, but anyways. Yeah, because we only know how to do it at the center of the circle. Right. Off center of the circle, as I said, is not for this year. That's for next year. But anyways, like I said, hopefully that kind of sets that one up there. How about we try something a little bit different here? How about number 23 then? 23 says, 23, where'd 23 go? They got a nice picture of it. 23. But these purple dots and X's are representing the current here. It says this in number 23. It says 4 very long parallel conductors carry equal amounts of current of 5 amps. I lost it. Let me go. 5 amps. In figure 23 is an in view of the conductor. The current direction is into the page at A and B. So that's why the X's are there, as indicated by the crosses, and out of the page at C and D, as indicated by the dots. Calculate the magnitude and the direction of the magnetic field at point P. P located in the center of this square, which is 20 centimeters on a side. Okay, so here we again have an infinite wire. We actually have 4, right? And so kind of drawing that, I would look at, say, an X here, call this A, come over here to the point P, and, well, I'll just put a dot there, and say, what would the direction of the magnetic field at point P be from A? All right, so here's this. Curl my hand, and I guess it would be like that, right? And so that would be the magnetic field I'll call A. How about down here from B? Grab it, curl, so I'm going to get a circle. And so this would be the magnetic field from point B. Fair enough? Now let's just stop on those two for a moment. Anything you can say about those two? Yeah, you can make this a little simpler on yourself if you look at the symmetry here, because these two wires have the same current and the point P is the same distance away. Hence, the strength of the magnetic field from A and B are the same. And so we've got two vectors that have the same magnitude. They're each angled down at a 45-degree angle here. And so the left-right components are going to cancel off, right? The vertical one's going to add up. So we don't have to worry about left and right, at least not yet. What about C? Wouldn't that be the direction of the magnetic field at C? I would take my right hand, I'd grab the wire thumb out of the board, and so I'd get a magnetic field going this way. And again, I would argue that I'm the same distance with the same current as A and B, so the magnitude of C is the same as the magnitude of A and B. And so I'll use that to my advantage in just a second. Because finally then I get to D. What direction is the magnetic field from D? And I would grab it with my right hand, thumb pointing out, curl it around. This would give me the magnetic field towards D. And again, I would argue that all of those have the same magnitude. So to save myself a little bit of work, I would say the X components cancel off here, right? So maybe I would say the magnetic field in the X direction is equal to 0, right? And in fact, the Y direction would be 4 times the Y component of just one of them, wouldn't it? They all have a component down. So there's no point in doing all 4 of them either. There's just saying down, 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 down. They all are down. So 4 times the Y component of A. All right, so how do I get the Y component of A? Well, I know that the strength of the magnetic field for my wire is given by that equation, right? And so that would represent this magnitude. But then I got to say something about that angle. And of course, they put it right at the center of the square, so that you'll realize that A is along the diagonals from C to B. And so this is at a 45-degree angle. So to get the vertical component, I want cosine of 45 degrees. All right, so there's the magnitude of A. That gives me the vertical component. That gives me 4 of them because I put them all together. And so there would be the total field in the Y direction. And I can call that a J hat or not. What if there was a 5th wire down the center, also carrying 5 amps? I'll just have it come out of the board. 5th wire coming out of the board, right there at the center of the wire. Would anything happen to wire number 5? Is there a force on wire number 5? It's going to take us back to the last chapter. Didn't we say that if you had a current in a magnetic field, there would be a force on it? So, if I take what we've done right now, this chapter, and add it together with what we did in the last chapter, where we said that there is a magnetic force, which is equal to the current times the length of the wire across the magnetic field, right? Then I would say, yes, there is a force on that fifth wire. The current would be its 5 amps, its length, its magnetic field is what I just got done calculating. So that'd be 4 mu naught pi 2 pi a cosine of 45 degrees. And then sine of, don't I take a cross product? Sine of what angle? Right, between the current and the field. Okay, so the current is going towards you. The field we just argued is down. So current is that way, field is down. That's 90 degrees. Okay, sine of 90 degrees. And it's a vector, so what direction is that force? Now what would happen to this wire? Well, current is that way. B is down, right? I cross B is in the x direction. Yeah, so this fifth wire is going to be pushed that way. It's going to be tug on. There's going to be a tug on these other ones too. I didn't ask about those. But you put a fifth wire there. And the point is, you put any two wires next to each other. The first wire creates a field. The second wire is then a current that is in the presence of a magnetic field because of the first wire. And there's going to be a force on it. And then we just have to take last chapter together with this chapter to figure out what is the force on that wire. Yeah?
Is it I cross B? Or no?
Well, it's written as L cross B, but the definition of the direction of L is the direction the current is flowing. Yeah. So an argument could be made that maybe you should put the vector symbol over the I. But since this tends to be a constant value, it's nice to leave it alone and then the direction, because if you have a wire that kind of snakes a little bit like this, its magnitude of the current stays the same, so you can pull it out of an integral, but the direction changes. So it's nice to have direction and current as two separate pieces. One more step here. Maybe I should put in the numbers I know. That fifth wire would be current. Well, I'll just put 5 amps, but I was thinking maybe I should have put a different current there to make sure it's clear in your mind what current we're talking about. This is the current from the fifth wire, the one that has a force on it. This is L. That could be a little misleading because I didn't tell you how long it is. So I'll tell you what. Why don't I move it to the other side and say, how much force per unit length? So if we make this whole thing 1 meter long or 2 meters long or 3 meters long, let's say it's 3 meters long. If I give you force per length, that's 5, then you would go 5 times 3. So it's probably best just to say force per length. So I'll move the L to the other side. Here's the 4. And I haven't been plugging any of these in, but I thought I would take a moment to just kind of remind you, what is the mu naught? Yeah, 4 pi times 10 to the negative 7, okay. There's my current of 5. There's my 2 pi. Cosine of 45 is root 2 over 2. But this A probably is worth discussing. What's A? Okay, it's this distance from here, and if this is a square at 0.2, this would be? Yeah, so this would be 0.1, and then this would be the hypotenuse of 0.1. So it's root 2 times 0.1, right? So root 2 times 0.1, which makes the root 2's cancel off, makes the 2 and the 2 cancel off with the 4, and things kind of reduce from there. The pi's cancel off, and we got a nice set of round numbers we could actually plug in for that case. Right. And so it was nice to us in the terms that it simplified. (28) doesn't have a picture. Let me read it for you. But it does, again, do a good illustration of what I just did for you today with Ampere's law. This happens to be a toroid. It says here, the magnetic coils in a Tokamak fusion reactor are in the shape of a toroid, having an inner radius of 0.7 and an outer radius of 1.3. So this toroid, and I'm not sure what the cross section looks like on the toroid here. Maybe I'll do a rectangular crossed section. And so here's my toroid. But they do say that this distance out here was 0.7 meters. This distance was 1.3 meters. I think if I read that right. That's a terrible picture. Does that making sense? Yeah, okay, so it's half of this thing. So here's my toroid, cross section, rectangular, curving back. Okay, so there's my toroid. I'll start again. The magnetic coils in a Tokamak fusion reactors are in the shape of a toroid having an inner radius of 0.7 and an outer radius of 1.3. The toroid is made out of 900 turns of large diameter wire, each which carries a current of, get this, 14,000 amps. Find the magnitude of the magnetic field inside the toroid along the inner edge of the inner radius and the edge of the outer radius. Okay? But other than that, it's kind of a plug and chug here. What was the equation then for the magnetic field from a toroid? Yeah, kind of looked like a straight wire, but amplified by the N, the number of turns in the toroid. So in our case, they wanted to know when you are near the inner edge and when you are near the outer edge. So variations. So we have 900 turns. We have 4 pi times 10 to the minus 7 for the mu naught. There's what really makes the field strong right there. It's not just 900 turns, it's 14,000 amps of current going through the crazy thing. Divided by the 2 pi, divided by the 0.7. And fortunately they cancel off a little bit, but I thought it would be a fun number to calculate. This is a huge field. So 900 times 2 times 10 to the negative 7 times 3,000 divided by 0.7 comes out to be 3.6 Tesla. Wow. And I should point out a Tesla is a huge field in and of itself. I know 3.6 doesn't sound that large, but you know, maybe don't think of it as 3.6, think of it as somebody went running and they just ran 3.6 marathons. So a marathon in itself is pretty big. Now go 3.6 of those and it's huge. And so we can get to another one. I'll just kind of real quickly do this one. Times 0.7 divided by 1.3. We're going to get a lower field at 1.94 Tesla when we put in a different radius there. And so there's the magnetic field from my toroid there. 31. 31 is back to the inside of a wire. I thought it would be a good one to do because one of you guys was asking while I was doing it. This one looks like what I did about an hour ago. What is the field inside a wire? But we had a uniform distribution to our current. This one does not. Look what 31 says here. 31 says, a long cylinder conductor of radius capital R carries a current I as shown in the figure. The current density being J, however, is not uniform across the cross-section of the conductor, but it does change with the radius according to the equation J equals BR, where B is some constant. In other words, as I draw this picture here and say, all right, here is my conductor. Flowing down the conductor is a current I, but what they're saying is the current has a surface effect. It tends to accumulate a little bit more on the edges, so that the current density is B times R. Okay? And so these little charges that are moved get pushed out. Which actually is an interesting discussion in itself, because isn't there a magnetic field inside the wire and we have charges moving, and so superconductors tend to the current just is getting pushed to the edges, okay? And it's probably because of its own self-magnetic field in there. But anyways, the current density is basically no current in the center and getting larger and larger, and so a lot of it is near the surface effect. But it's not uniform. That's the point of picking this one here. It says, find an expression for the magnetic field when you are a distance r from the center of wire, both inside and outside of the wire. All right, so maybe I'll start on the inside first. That's really the significant difference between the uniform and non-uniform. Once you're outside the wire, you still have a current of I. So as we'll see, there really is no change on the outside. What number did I say this was? Number 31. 31? Okay. So number 31 is saying, all right, if I take the magnetic field and I integrate it around an Amperean loop, I will get this, the current inside. And so let me start off by saying, let's look at R less than capital R. And so my Amperean loop, and they don't really show one in there, but my Amperean loop is going to be something like this. Right? Inside of the wire, yeah.
Is that lowercase b just some constant?
Yeah, and it's b is a constant. And they didn't even tell me what it is, so they just say b is a constant.
So it's not the same thing.
But it's not the same as capital B. Is that what you mean? Yeah, no, yeah, it's just some constant. Yeah. Maybe would have been a better choice if they didn't use, well, at least they used uppercase and lowercase, yeah. All right, but again, same argument. Like I said, I thought it'd be a good example. We've done a couple of Ampere's law, but they're worth seeing, even though in theory this is supposed to be straightforward because we did all this for Gauss's law, right? So it's kind of the same arguments. All right, so the symmetry is that big one. Take the dot product, all right? And so I will go b times ds times cosine theta. So again, let me start with the left-hand side. Take the dot product, but again, hopefully you can see from the argument of symmetry, they were nice to us. Even though I don't have a uniform, and that's what I want you to see. I do not have a uniform current density. Fair enough? But I do have a current density that gets bigger no matter what direction in R you go. So if you picture yourself standing on this Amperean loop right here, and compare that to here or to here, you will see the same current distribution. Not a uniform current distribution, but you will see, as you stand on the loop looking towards the center, you will see more current behind you than in front of you, and it would be around that same thing. But if you stand somewhere else on that Amperean loop looking in, you're going to see a lot more behind you than in front of you in the same pattern. And it's because it's the same pattern of current, it must create the same field. And that's been our argument since we did Gauss's law. And I don't know what that value is. I do expect it's going to be a little more complicated than what we got for a uniform charge distribution, but I can still say that it has the same value on my ambient loop. And again, I am not saying that the magnetic field is the same everywhere in the whole wire. I mean, it wasn't even the same everywhere inside the whole wire for a uniform current distribution. And so it's certainly not going to be the same magnetic field everywhere inside that wire now. But I am saying it's the same on the ambient loop, and that's the difference here. It's the same on that ambient loop. All right. Also, the direction of the magnetic field. That really wouldn't change either. We even though our current distribution is not uniform, at least we would argue that take your right hand anywhere on this and you're going to get it all in that same perpendicular direction to the current flowing. So even though we don't have a uniform charge distribution, it's all flowing the same direction, and hence the direction of the field is just like we did before. So yes, this is going to be cosine of 0 degrees. So that I kind of expect here. So this side of the equation is still going to become b times 2 pi r. So really haven't seen any change here in terms of my calculation. But the other side of the equation definitely is where the change is. This other side of the equation is mu naught, and then to get the current inside, I've got to take the current density, starting maybe at a small radius, and add it up, 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 add it up. So I am going to take a small area and say how much current goes through that ring. And that's what I mean. What is the current density at that point? Well, that's what the equation is for. So I guess I could write this then as mu naught times the integral of b r, right? It's not a constant. I can't pull it out of the integral. We did an hour ago pull it out of the integral because it was a constant, but now it's not. So I leave it inside the integral. That's the only difference. But it's going to force me to actually think about dA again. dA is what? Well, maybe I should blow this up a little bit more. If I take that picture and I take a ring and I'm saying how much current goes through that ring having an area of dA, isn't that the circumference of the ring times the thickness of the ring? Where the thickness of the ring is the dr, and then the circumference. So that's why the current density times the thickness is a little bit of current, which is why when you sum it up, you get the total current that goes through that ring. So that's the important step. And again, like we did with Gauss's law, although it's been a while since we've done Gauss's law, I can write this as 2 pi r dr. And then I would be adding it up from 0 to little r, right? I'm not going to add up all the way to the edge of the wire because I want to know how much goes through my ambient loop. And so pulling my constants out, I've got the mu, I've got a 2 pi, I've got a b, and then I'm left with an r squared, which then when you cube it, an r squared, when you integrate it, becomes r cubed over 3. And so now it looks like a 2 pi cancels off. It looks like an r cancels off, and I get what they're looking for here is what is the magnetic field inside. It would be that. And a plot then would be quadratic. And so it would go something like that, at least until I got to the edge of the wire. And so I get a different effect of the magnetic field. So here is a different equation because I have a different current distribution, okay, for the magnetic field. Now, what about the outside here? Yeah, on the outside, so when R is greater than capital R, I can again start with Ampere's law. And therefore, I would draw an Ampean loop on the outside of my wire. But I would make the same type of arguments that I did for the inside of the wire. That first I would take the dot product. The dot product would then allow this B to be a constant, I mean at least a number that I can pull out if I can prove that it's a constant. And that's our symmetry argument, that it is. So I'll pull it out. And the angle's still 0 degrees. So on the left-hand side here, I still end up with B times 2 pi r. On the right-hand side, I really just end up with total current. Right? And so I really don't have anything different here between outside of the wire and inside of the wire. I get the same equation. Now maybe I could take another step. I don't think I need to, but just since we got just a second left, I'll do it here. But it says, you know, what is the magnetic field? And they don't say if I should label it in terms of I or, you know, the J, which has the B in it. So in this case, I left it with a B. In this case, I left it with total current. I probably should be consistent. I should either probably turn the B into total current or total current into B's. And so it doesn't matter which way I should go because I don't think they're very clear on that. But wouldn't the total current then be the summation of the little current, which is the JDA, where we go from 0 to capital R, right? And so the J becomes BR, the DA is 2 pi R dr, 0 to capital R. And so this becomes 2 pi B, R squared becomes R cubed over 3. And so that's the total. So if I wanted to make it look similar to my other answer, I might replace total current with 2 pi times B times capital R cubed over 3. And I get mu naught B R cubed over 3R. And so the rest of this plot would now decrease with a 1 over R square value. And you can see when little r equals big R, I get the same thing. So the field right on the edge of the wire matches. The one on the inside gets bigger until it starts to get weaker on the outside. So the strongest place of the field is right there on the surface of it. And as a side note, this is the unfortunate physics of semiconductors, superconductors. We talked about superconductors before, and they don't work when the temperature gets higher. They also don't work when the field gets stronger. So even if we invented superconductors that can operate at room temperature, and we tried to put 14,000 amps through them, guess what's going to happen? They're going to make their own strong magnetic field, and they're not going to be superconductors anymore. So we've got two big challenges to overcome: their temperature and their magnetic field effects.
Superconductors